Thank you. I'm going to talk a little bit about processors for intelligence. I'm not going to tell you how to build a processor for intelligence. You'll have to wait a year or two for that. But at least I'm going to discuss what characteristics processing for intelligent applications have, and some of the characteristics required of machines that might efficiently support intelligence. I'm going to keep using that word. I'm not going to use the word smart at all, apart from just then. Smart, obviously, that just means complicated in today's world. I have a complicated phone, but it's not intelligent. It does not help me solve problems. It cannot do anything that software engineers and systems engineers did not foresee. So that's the distinction I make. I should say I am the CTO of XMOS these days, having taken over from Dave after many stalwart years. What I'm talking about here is not what XMOS are currently doing, but you can read into what I say, whatever you like, about what we might do in the future. In fact, you've heard what we're currently doing this morning, so you don't want to hear it again. Right, we live in interesting times. A couple of useful things are happening in semiconductors. I say useful because I think design engineers become more valuable as a result of these, and that's why they're useful to us. The first thing, of course, is that some years ago now, in fact around about 2005, 90 nanometer process generation, Dennard's scaling stopped. It stopped abruptly. What stopped it was the inability to lower the VT any further, and therefore the inability to lower the main power supply. And as we all know, that's why we're here, it means we can't build faster microprocessors, we just have to build more of them. David would like to build 1,000, possibly 10,000 if he could get away with it. I'm sure we'll all get there, possibly not as fast as Dave would like, but certainly we need to build more if we want to do more stuff on silicon. The other thing, which is slightly more contentious, is whether or not Moore's law is ending. Certainly scaling is not ending. That won't end for quite some time. But scaling at constant cost on a 2 to 3 year time base for each doubling of density, that's certainly over. So it's at least the end of Moore's law as he originally proposed it, which is constant cost. Well, he originally said 18 months, but let's be generous and say constant cost 2 years. That means that if you do a poor design now, unlike 5 or 10 years ago, you will not be rescued by the next process node or the one after that. If you do a poor design now or an inefficient design for your application, you're going to be stuck with it. That's great, because it means that you will get paid more for doing good design. Engineers will become more valuable. Fantastic. But the third thing, I think, actually is more important than either of these two. These two change our world, but the third thing changes everyone's world. And that is that the sort of applications that we now want to use computers for require intelligence. And I'm going to tell you what that means. This graph, I'm sure you've all seen it. This is various companies' microprocessors, clock speed over time. That's 2005, that's 90 nanometers. Stopped, absolutely dead. If any of you follow the ITRS roadmap, it was quite hilarious up until about here, I think. I think they went up to about 30 gigahertz before they acknowledged that in fact everyone had stopped at 3. So I contend that, or we contend, I actually didn't make that very pretty picture, that comes from my marketing colleague. We contend that a new type of computing is about to arrive, in fact arguably is already arriving. We've called it intelligent computing. Everyone has their own version of the story leading up to this: mainframes, personal computers, mobiles, etc. The new bit's intelligent computing. What I mean by that, now that I should say that psychologists can't agree on a definition of intelligence, so I'm certainly not going to attempt to define it for you, but practically speaking, what it means is that we're now trying to solve problems which don't have algorithmic tractable answers. Either because they're NP-hard, so there is no algorithm, apart from exhaustive search, which is impractical in most cases. Or we just can't conceive an algorithm. The canonical example is recognize your mother. We can all do it, none of us can write the algorithm. Or it's too expensive to run an algorithm, that sometimes occurs. Or where there's simply not enough input information for an algorithm to yield a result that is exact. And the key point here is that intelligent systems are supposed to try to help us with the job of judgment. Today all computers produced up until now, from the very first one in 1943 up until now, have been done, completely done. A human has decided how to solve an algorithm. They've codified the method of solution as a program, as we all know, and they just run the program. The computer does not help us solve problems. Intelligent computers will help us solve problems. They will be part of the solution. Here's the canonical case of not enough information. The process at the top, that's a, I'm not sure what that is, I should ask one of the NVIDIA guys, is that a Kepler? It's one of those snazzy teraflop GPUs they make. One of the most complicated chips in the world today, an absolute masterpiece of silicon engineering. And its job is to take a 3D model invented by a games designer of a dinosaur or something, with a big gun, probably, and to project or compute 2D projections of what that 3D model would look like if you stood in a particular place, so that it can be rendered onto your screen. We call that job graphics. It requires teraflops of compute, and that's a toy. But it's also the biggest chip we know how to make. The job in the opposite direction is called vision. Take some 2D views from a camera or from your eyes and compute the 3D world. Now there's not enough information, in fact. Even if you had a lot of 2D snapshots, there wouldn't be enough information to infer the 3D world. So that task is impossible. However, we can all do it, otherwise we'd run into each other. We do it because we exercise intelligence. A task in a computational sense is very, very, very much harder than going the other way. So if graphics requires teraflops, vision requires exaflops or petaflops, or no, other way around. What comes after exa? Yottaflops. Now, as we know, Moore's law is stopped, Dennard scaling is stopped, so we will never have yottaflops in silicon. So we have to tackle this in some better way. And again, this is why we require architectures that are good at intelligence. Intelligence will touch a lot of applications. In fact, already it's ubiquitous in the cloud. I'm not sure how many people are fully aware of that, but every time you shop online, every time you go onto Amazon or whatever, literally hundreds of servers click into gear to try and match you to other people who look at similar things to you. They try and match the product that you're looking at to similar products. And they do this in a fraction of a second so that they can splash onto your screen other things that you might like to buy. They're then doing live price comparisons, of course, with other products or with that product being sold by other people all over the web, and trying to dynamically adapt the pricing for you as well. All of this is it is intelligent computing, codified on unintelligent architectures, but it's intelligent computing. It's been ubiquitous in the cloud for 10 to 15 years, and it started off pretty simple. The original pseudo-clever collaborative filtering algorithms are very explained to you in 2 minutes. They're all engineers. But now, actually, these are pretty complex, some of these algorithms. Very sophisticated indeed, which is why they need hundreds of servers for a fraction of a second. And I believe, in fact, it's a no-brainer to me, that these processes, these intelligent processes, will migrate into embedded scenarios as well. And these applications that I've listed are all things that require intelligence. They're all things which are not tractable to algorithm. Vision I've just discussed. Vision is all about estimation. It's all about judgment, and judgment in particular based on prior experience, based on learning. And that's what really distinguishes intelligence. I'll talk about that a bit further in a minute. Robot navigation is in the same category. Now, by robot, I mean anything that moves, frankly. Your car. Cars in Europe are already, next year, I believe, new models in Europe have to have some intelligent features. They have to have forward anti-collision radar, for example. You can already buy a car from Volvo or BMW that is able to read road signs, spot traffic junctions, recognize bicycles, recognize pedestrians, and signal warnings if it thinks you're going too fast or you're likely to intersect with their trajectory. So robots, cars is the big ultimate robot, but we will see lots of smaller examples of that. And the various steps involved in a robot's life, the simple things like working out what its environment looks like, where it is in that environment, planning how it's going to move. I don't know how many of you have ever considered a robot arm. I mean, our arm obviously has various joints, various links. If I want to pick something up, it seems obvious to me that I'd pick it up in a certain way, but actually there are millions of ways I could pick it up. And to a robot, it's actually quite a complex task to work out which of those ways is optimal. Any sort of control system with a high degree of freedom, we are discovering, is easier to train than it is to program. For years, people have been trying to write programs that allow legged robots to walk. They've been trying to define the algorithm for walking. And then some machine learning guys came along. When I say intelligence, some people call that machine learning. I'm going to stick with intelligence. So machine learning guys come along. They know nothing about control theory. They throw away all the knowledge of control theory mathematics, and they apply a machine learning approach to the problem. They simply instrument the joint positions. They tell the robot what condition it's in as it falls over, and they get it to keep trying. And each time it tries, it can adapt a machine learning model of how to balance. And you know what? It can learn to walk faster than you can write a program to tell it how to walk. I have seen in Cambridge, you'll find this on the web if you look, I've seen a robot learn to unicycle in 1 minute. Humans can't do that. And in fact, the robot couldn't do that using control theory. But using machine learning, it can. And it took an awful lot of CPU cluster to get it to do that with today's CPU. Sensor information, extraction and fusion, any sorts of sensors. Think simple things in your house. The famous Nest smoke alarm. It sits on the ceiling, so it's a bit difficult to get to. So when it goes off accidentally, or even because there's smoke, you want the user to be able to turn it off. So they built in a thing that would recognize waving motions to turn it off. And then there was a big recall problem because it turned itself off when people blew their nose or something. Something that wasn't waving at the smoke alarm sensor. But that really trivial interaction with a machine requires tremendous sophistication. The machine has to see the scenario in play and distinguish it from countless other scenarios. And there's nothing exact about its computation. It's going to form an approximate judgment that you just waved at it, and therefore you want it to turn off. Speech, dialogue, gesture interfaces, these are all examples. So what do we mean by intelligence? What's the actual mechanism at play? What really distinguishes intelligent machines from unintelligent machines is the use of models. So we're used to machine's behavior, a processor's behavior, being entirely defined by a program. But in intelligence, as we've said, the problem is not tractable to algorithm, therefore you can't entirely define it by a program. So you have to have something else. And the something else is a model. The model must be learned. There's usually a program as well, of course. And in fact, the algorithm for learning is usually defined by a program. That's okay. The learning algorithms are tractable. It's just that the learned behavior is often not tractable. So there are two related processes. Actually, there are 4 or 5, but I've simplified. Two related processes here. The first is the acquisition of a model by experience. That could be supervised, it could be unsupervised. And the second is having acquired a model, which is usually a model of correlations between observable parameters. There is a process of inference that allows you to take further sensory data and work out things about what's happening. And the results of this are always probabilistic. There is no certainty in an algorithmically intractable problem situation, obviously. So the result must be a probability distribution. It's a distribution over various things that might be going on. So there's always a final task, which is to decide how to react to that probability distribution. Your car driver assistance system might decide that there is a 0.001% chance that the thing in front of you is a person and not a paper bag. The policy decides whether to apply the brakes. That's obviously quite a difficult thing, and I'm glad that Glenn will be taking care of that. I'm not going to talk about policy. In fact, it's a whole branch of science, decision theory on its own. But I'm interested in the first part, the machine learning process and the inference process. So the key characteristics, there's always a model. It has to be learned. It could be learned offline, and then the machine itself in action could just be inferring. So the walking robot would be a good example. Once you've trained one robot to walk, they can all walk. That's okay. Doesn't need to do any more learning about walking, it just needs to enact walking. So there's always a model. The model is always a model of probabilities. It's usually very high dimensional. A face recognizer, a simple thing for recognizing your face. Suppose in the future I get into my car and the era of the car key is behind me. I think, to me, there are two things which are just anachronistic. One's car keys, and the other thing's telephone numbers. I don't understand why we have either of those now, but anyway. I get into my car, I want to drive it away. It has the benefit of my hands on the steering wheel, my bum on the seat, and my face in front of it. It uses whatever sensors it needs to work out whether it's me. It's a probability judgment, whether it's me or not. Really simple thing. So, let me give you some examples. Actually, I used these variants, these foils, a few months ago, and this thing hadn't been released. I guess all of you might have seen the release of this a couple of weeks ago. This is the new Dyson 360i robotic vacuum cleaner. There have been previous robotic vacuum cleaners. They haven't been intelligent. This one is intelligent. This knocks the others into a cocked hat. This will compute where it is in your room. It will plan its vacuum cleaning, and it will do it in an orderly manner. Apparently, according to Dyson, it also has very good suction, but I'm not interested in suction. The point is, it works out how to do its job. It has, on the top, a camera. I think it's monocular, don't know, haven't done a teardown yet. But it's 360 degrees, that's why they call it 360i, of course. And think about how a robot navigates around an unknown environment. You open its eyes, you take it out of the box, open its eyes, it's in a room, never seen it before. What it really needs to do is acquire a map of the room and locate itself in the map. Now, unfortunately, a bit of chicken and egg involved in that, because if I knew where I was, I could perhaps measure my distance to other objects by my sensors, and then I could build a map. Or if I had a map, I could work out where I was. But if you have neither, where do you start? Well, usually you start by locating some landmarks. They can be interesting textures. They can be corners of doors. They could be the sofa. They could be the dog. And then I move a bit, and I see how the landmarks move in my field of view. And then I move a bit more, and I see how they move. And gradually I can build up a picture not only of what the environment looks like, but also of where I am. And it's probabilistic, and actually all sorts of things contrive to get in the way. Landmarks may suddenly be obscured, they may disappear. The dog may get up and walk away. And this is just a robot vacuum cleaner. It gets a lot more complicated for cars, which have to do essentially the same job. A self-driving car has to do the same job. The thing is, whereas a vacuum cleaner can gradually learn your living room, and then it's only got to learn sort of little changes to your living room as you move the furniture or that sort of thing. A car, crikey, it's driving down roads it's never seen before. It's building maps of where everything is to either side of it and in front of it. And as soon as it's passed all those, it's throwing all that lot away and building a new map. And it's got to do that at, well, depends who you are, but potentially at hundreds of miles per hour. anyway, back to the robot vacuum cleaner. Robots are cheap things, so when they try to determine how far away the bookcase is, all this thing's got is a camera. I think it's monocular, like I said, so actually to get a stereo image it needs to have multiple viewpoints, and then it can use parallax to try and work out how far away the bookcase is. Even that's a probabilistic judgment, and it's quite difficult to do that accurately. So the sensor information is noisy and has a probability distribution. And also when it says, right now, motor wheels move forward 10 meters in 30 degree to forward direction, those two things may be inaccurate as well. Wheels may be slipping on the carpet, and it's, instead of moving at 30 degrees, it might move at 25. So all these things have to be factored into what turns out to be a graph, which represents a joint probability distribution over many, many dimensions. The dimensions are primarily the locations, the successive locations of the robot. This is just 2 dimensions, so there's not much difference between location and pose. For a helicopter, it's a lot more complicated. And the apparent observations of the landmarks, some of which may from time to time disappear from view. And as you can see, I've assumed here we have a Gaussian distribution whenever we make a distance measurement. We have a 2-dimensional Gaussian whenever I make a move. But gradually I build up this graph of data, and with enough links and enough points, I can perform what is essentially an energy minimization optimization algorithm. There are many, many different algorithms for SLAM, and I can shrink the probability spread such that I have a fairly accurate picture of where I am and where everything else is in the room. And then I can plan my vacuum cleaning strategy. So it's an amazingly complicated process for just a vacuum cleaner. And hats off to Dyson for delivering the first one at consumer price point. There'll be many, many more. Now I expect, there's no special silicon in that vacuum cleaner. It'll be a commodity ARM processor of some sort, I expect. I don't know. So obviously today I can do that in an ARM. If I want to do that job in a car, driving not even at hundreds of miles an hour, but just say at 30 miles an hour, today I need a server cluster to do anything that approaches navigating in real time. In future, of course, I want to do that for $5. How do I do that? I need to build better machines. So let me give you another example, speech dialogue. There are many sorts of machines in future you might want to talk to, but for me the most compelling case again is the car. I don't know if have you seen a Tesla inside? So Tesla is very high-tech, very impressive electric motor car. California is full of them now. They've done away with most of the knobs and buttons on the console, and they've replaced it with what can only be described as an oversized iPad. It's about yay big. And the idea is that in order to control any of the car's features, like where you want to go, or what the temperature is, or even probably move your seats, I don't know, you interact with this iPad type thing. And it's touch sensitive, and it's got all sorts of icons and stuff. But how are you supposed to do that when you're driving? To me, it's a mystery. The one type of interface you have available when you're supposed to be concentrating on the road is your voice and your ears. In other words, talk to your car. So it turns out speech translation, recognition and translation of speech into typed sentences is pretty good. In a noisy environment, sometimes it's not perfect, but it's pretty good. But it may actually have got to the point where it's as good as we can get. Maybe noise limited, it may be information theoretic limited. If I talk to Siri on my phone, it usually does quite a good job of reproducing what I said. So it will pick up sounds, correlate those with its dictionary of words, correlate words with its understanding of English grammar, and produce a sentence, a well-formed sentence. So that's fine. Translation. The trouble is, what I say isn't usually a very good indicator of what I mean, unless you have a pretty accurate model of what you thought I might be about to say. And that's where the dialogue aspect comes in. We need to build the next layer up, the layer in which the machine's not trying to track what you say, it's trying to track what you mean. what you're talking about. And for things like cars, which don't have much conversational state space, they don't need to talk about religion or politics or sex. They just need to talk about cabin temperature and where you want to go and what's on the hi-fi, as in my example. So the conversational state space there, actually, we've got a reasonably good chance of being able to track where we are in it. And if we can do that fast enough that it can respond back to me and ask me clarifying questions, in other words, engage in dialogue at a natural speed, then we can close the loop on understanding, because if it gets confused, it can ask clarifiers. So as soon as we get to the point where we have both of those things, in other words, we have a machine trying to track understanding, not just grammar and words, and we do it fast enough to enable natural speed dialogue, then we have a loop for exchanging understanding between the human and the machine. Now there are prototypes that will do this as well. They run, again, on server clusters today. There are some simple examples. There's a trial that runs in Cambridge at the moment. You can ring up a phone number and ask for hotels and restaurants and which type of food you want to eat in your restaurant. You can tell it which part of Cambridge you're in, and it will try and recommend places to eat. That will actually run on a server. Hey, Mike, hi. But nevertheless, a server, a $200 chip, we want that to be in our smoke alarm, probably. I want to have a conversation with my smoke alarm. I want that feature to be $1. A final example, this is probably the world's first mass consumer market machine learning device. It doesn't actually do online learning, it just does the inference online. The learning was done offline. It has a model, quite a big model, of skeletons, human skeletons, and how they articulate. So it knows which poses I can put my skeleton in. And it was trained from actually 200,000 actor poses with the little light dots on them, and then they interpolated those to make a training set for 1 million, and took 24,000 server hours to learn a model of how skeletons articulate. And then in your living room, what it does, it projects infrared speckle patterns at you. You can't see them, of course, they're infrared. And its infrared camera picks up the distortion of those speckle patterns, uses parallax disparity to infer an estimate of depth, correlates that with its model of how your skeleton might articulate, and works out where you are. And, projects that back to you on a TV or whatever it does. I haven't got one, actually. I have played with one. And they've sold millions of these. In fact, this was supposed to be the world's fastest selling consumer electronics device. I can't remember what the numbers, something like 6 million in the first 8 weeks or something. Anyway, it's in the living room, so it's machine learning live today. There's no learning in that, but there's machine inference, and it will. So the compute budget for that was 15% of the CPU cycles of the Xbox chipset originally, which was a 3-chip ASIC set, but it probably has no more horsepower than a typical high-end mobile phone today. So clearly, once the skeleton's been learned, the job can be done quite quickly. Right, what are the characteristics that all these forms of processing have in common, such that we might shrink our server clusters into a $5 or $1 commodity chip by building a better machine to support it? Well, we've talked about probabilities. Probability data types and probabilistic calculations are absolutely fundamental. There is no certainty in any of these calculations. They all deal with probability distributions. They can be parametric in some cases, they can be sample sets, they can be enumerated histograms. The data structures are large. The face recognizer in your car typically extracts features from your face. Some are obvious, like eye separation and where your nose is relative to your eyes. Many are not obvious. They're learned autonomously by the machine. Typical face recognizer today, about 50,000 features. Each feature is a dimension in a high-dimensional optimization space. So you built a model of a surface in 50,000 dimensions when learning faces. And when I get in my car, it's got to compare my facial features with that model and see if they're close enough. But it's going to let me drive the car. A typical a hidden Markov model of language understanding to do, top quality speech recognition. That's just the recognition bit I mentioned earlier. Typically 1 million parameters. That'll be for pretty much any speaker. But it wouldn't be many fewer parameters if it was just focused on one speaker. So these models are big, and bigness would be a really big problem if they weren't also sparse. In other words, it's not, although they're very, very high dimensional, 50,000 dimensions, almost all the parameters along any one of those dimensions are 0. Extremely sparsely occupied high dimensional space. And the obvious way to represent such a model is with a graph, a sparse graph. Graphs and matrices, they are dual representations of it. I've shown here a sparse matrix vector multiply and what it would look like as a graph. If the matrix were dense, then there would be edges from every to every. If it's sparse, it just means there are fewer edges. But you can see the more sparse you become, the more natural it is to consider this thing as a graph. Now, one property that brings, in fact the most important property, is that there is zero access locality to that structure stored in memory, however you store it. That is a computer science theoretic proved result. There is no storage arrangement that allows for locality of access with arbitrary, irregular sparsity. Generally what we need to do on that graph is some sort of energy minimization over the surface. In other words, find a minimum in this high-dimensional surface. It has infinite available parallelism. Parallelism is at least as high as the dimensionality of the space, often higher. And the amount of communication between each piece of compute is very, very high. Now this is completely the opposite direction to the direction that GPUs have taken us in, where the amount of compute is very high relative to the amount of communication. Just to show you what the impacts of no access locality are. First of all, caches are harmful. Whenever you go and fetch a 32-bit floating point value, you miss your first level cache, so you have to get that line. That misses the second level cache, you have to get the second level line, and probably you go off to the DRAM and fetch 4 kilobytes. You probably fetch a page for every 4 bytes that you actually need. This is the effect of matrix multiplies, sparse and dense, so dense at the top, sparse at the bottom, on 2 scalar machines. One's a Xeon, one's a PowerPC. You can see that the fall off in performance for these are large ones. You can see the dimensionality at the bottom. The fall off in performance caused entirely by the caches is at least 100 to 1,000x. The other thing that we have increasingly built into our processor designs, because we like locality and we like to exploit it, we've built in vectors. We like to think whenever we fetch some data, we'll fetch a whole big chunk of it, and then we can compute on that all at once. So these are our 2 finest chips, the Xeon Phi Knight's Corner, which is over a teraflop of compute, and that Kepler thing again, 1.3 teraflops of compute. They're both a couple of 100 watts. They both cost a couple of $100 probably. They're huge. They're fantastic machines. And teraflops. Yes. Sparse matrix vector multiply. This is actually from a paper by Intel and Georgia Tech. And its purpose was to show that Knight's Corner was just as good as the GPUs. And you can see the blue bars and the green bars are about the same. So roughly they did. They're both really bad. 25 gigaflops from your teraflop machine. And these are the machines that are doing the machine learning in the cloud when you go and do your e-shopping today. They're doing it on machines like this. And they're using teraflop machines to get tens of gigaflops. So what we need to do is we need to build machines that give you that tens of gigaflops without all the rest of the clutter. How do you do that? Well, at least you take out the caches and you take out the vectors. You probably have to do more than that, to be honest. So my contention is that there will be a third type of machine. It won't displace the other 2 types of machines. There'll be CPUs, there'll probably be more than one of them. And task parallelism lives there. But data parallelism, which is a lot of the parallelism that's available in a lot of the applications that we point out, comes in 2 flavors. It comes in dense and sparse. We have the dense machines, they're GPUs. and increasingly wide SIMD data files on CPUs, frankly. It's all the same. We don't have a sparse machine. That's what we need to build intelligent applications. Software will have to change. He's standing there, so I'm going to skip over that. It'll have to change in obvious ways. The last bullet there is worth mentioning. Specification, debug, verification will all have to accommodate the fact that the result is probabilistic. It may even be stochastic. I don't know how you do that. Interesting challenge to those software engineers in the crowd. And how we program these things, well, there is a lot of interesting work going on in the cloud that I expect will migrate into embedded. Google set the ball rolling 3 or 4 years ago now with the launch of a thing called Praegle, which is a graph processing framework for machine learning. They're now moving their entire software infrastructure over from what was originally MapReduce-centric to Praegle. So if Google are doing that today, if you weren't convinced by everything else I said, you can be convinced by that bit. And if that stuff's happening with graph frameworks today in the cloud, then it'll be happening in your car next. And final point, really. Anyone, I mean, crikey, I spent 10 years in cellular business, and that was quite enough. Anyone who believes that you're going to have a permanent high bandwidth connection to any moving machine of any sort at any point in the future is smoking something, frankly. Certainly, I don't want any part of my car, whether, never mind the braking system, even the hi-fi, I don't want it to ever tell me that it can't change track because it can't access the cloud. So intelligence will be embedded. It will not all be centralized. And even Cisco are now espousing this idea that, in fact, intelligence has to exist at all layers of the hierarchy. They call it fog. The idea of the cloud that's come down to the ground. It's the Cisco fog. Maybe not the best bit of marketing in the world, but oh yeah, I threw that one in for fun. Machine's not intelligent unless it can make judgments, in which case it has the capacity to correctly compute incorrect answers. Self-driving cars will crash. The only reason we will like them and accept them is because they will crash less often than humans, but they will crash. There you go. That's Colossus on the left, the first programmable electronic computer, 1943, the onset of intelligence, and those two other minor details to do with the running out of steam of semiconductors is the biggest change, and therefore the biggest opportunity in computing since that machine was built 71 years ago. Thank you.
Thank you, Simon. I'm wondering if oh, great money, really. We do have time for one question, Simon. I did notice the point about the verification challenge in that as well. So,
it's going to take a lot more engineers, Mike, and they're probably going to be really expensive.
All the right words. We do have one question, that's good. Paddy, come and save us, Paddy, from this.
I'm not expecting much of an answer, but with intelligence you've got liability as well.
It's all right, though.
I'm expecting a short answer, by the way. So.
There's the answer. There's the answer. AIG will offer insurance.
Oh, well.
Me.
Yes, there you are. 2 adverts for 1. Okay, we are going to go straight into the talk. We're going to thank you, Simon. Thanks, Simon, one more time. Thank you.